Today's topic is highly vital because it has become the part of your past paper 5 to 6 times. The topic is Nernst Heat theorem. In the earlier development of chemical thermodynamics, the difficult task is to make a relationship between the free energy and the enthalpy, means that to derive the free energy or Gibbs free energy from the thermal data. So before that we will discuss a short about the relation between them with the help of different equation that will lead towards the determination of Nernst Heat theorem. So first thing to determine here is that the Gibbs-Helmholtz equation, it says that the free energy is equal to H plus T differential F over differential T at the constant pressure. Let's talk about the other part of the derivation. Here when we take the finite change, mean the differential, then we will apply delta or in the free energy delta on the enthalpy constant delta on the this factor also, that is also free energy. So the equation become in this way. When this delta H goes to the left side, the equation appear in this form. And if we apply the condition where we are saying that the temperature is 0 K at that form, you know that when 0 will be put in this value, when the 0 divides to anything it becomes 0. So we can say that the right side becomes 0 and only left side equation will be remaining. So if we take this enthalpy factor on the right side, the equation become in this way. When the temperature approaches to 0, then change in Gibbs energy of the process become equal to the change in enthalpy that we have studied in this form, in this simple equation. So if we apply the conditions where we are saying that in that condition the free energy is becoming equal to the enthalpy when the temperature is approaching to 0. So when we apply this limit or condition, the equation is limit T approaches to 0, delta F is equal to limit T approaches to 0, delta H. That is about the explanation of the theoretical concept that we have built it now. Okay, next is that W. Nernst 1906 found experimentally that quantitative relationship, this one quantitative relationship that was here, this quantitative relationship decreases with the decrease in temperature. Okay, this will cause decrease as the temperature is decreasing, this factor will also go on increasing, and when the temperature reaches to the 0, this will also become 0. This is all about the Nernst Heat theorem. If we write it mathematically, it will appear in this way, because we have said in this equation that delta F is equal to delta H. In that case where the T is approaching towards 0, so it means that this whole factor is equal to 0 when temperature is approaching to 0, and we know that delta F is equal to delta H. So we can write this left side equation same for the delta H. That is why we are putting this value, we are using this value along with the limiting factor, and then again we are using this form on the right side for the enthalpy, because we have said earlier, because there that the free energy is equal to enthalpy, that is why we are writing this factor coming equal to 0 when T approaches to 0, and then we are applying the same term or condition to the enthalpy where delta F is replaced only with the delta H, all other factors are same, and we are saying that simply delta F is equal to delta H, and this both of these are coming 0 when the T approaches to 0. This was all about the Nernst Heat theorem, which was saying that when the temperature decreases, this factor decreases. This factor means the differential of the free energy ratio with the temperature at constant pressure will decrease. Same we have said that the free energy is equal to enthalpy. In the same sense, it means that the enthalpy ratio with the temperature at the constant pressure will also decrease, right? So it means that both of these factors will decrease with the decrease in the temperature, and it will go to 0 if the temperature approaches to 0 Kelvin. This portion I am taking from the Maxwell relation to make you understand this today's equation, Nernst equation. First of all, you must know that Gibbs free energy is equal, F is equal to H minus Ts. When we differentiate it, it become in this way that I have make you understand in the previous lecture. And then we apply the value, put the value of dH in the equation, then the dH value TdS plus VdP. So it become minus, and the remaining factor minus TdS minus dt become as in the same way, and the equation may become in this way because the tds and plus and minus are cancelled out and remaining equation is this. Why I am telling you this again, just keep it remember that f is equal to h minus ts, and after taking the differential it is becoming in this way, that we are going to use it today. I have told you that f is equal to h minus ts in the Maxwell relation, and after taking the differential the equation appear in this way. At constant pressure this factor is equal to minus s minus entropy. We have said this in the previous equation of the Maxwell, where I would like to show you first. This is here. This is here where we have said this factor, that is differential of the force and temperature at the constant pressure, it's becoming equal to the entropy. So the same factor we are going to use by taking the fourth segment. This is the fourth segment of the Maxwell relations. So by taking the Maxwell relation at the fourth fragment where we have said this thing, we will apply it in today's equation. So by keeping remember this thing, we will apply here. So if we take the differential of all the factor, differential of free energy, differential of entropy, those, so the differential become in this way, and according to the equation the left hand side of the equation is equal to 0 when the temperature approaches to 0. You have said this many times and have understood this thing, that this factor become equal to 0 when the t approaches to 0, because when we divide this factor with the 0 value, so when we write the 0 or something here, value is written on the top and the 0 is written on the downside, so the value becomes 0. So that is why we are saying that when we divide something with 0, so it becomes 0. Finally we are saying that then when approaches the absolute temperature approaches 0, so the value or this left side factor becoming 0. So only the right side is factor to be studied. In the case of temperature approaches to 0, its phenomena is to be understood, because the left side is already understood that the left side will become 0 finally. So only the right side is about that where the change is occurring. Change means variation will occur. So when we apply the condition that limiting factor temperature approaches to 0, delta S is equal to 0, because the left side is becoming 0, that why we are putting here 0. So limiting factor T approaches to 0 means that variation mean the change from one side to another, from one to another, means that the first entropy that was lesser and it is getting subtract from the higher entropy, that is S2, because with the passage of time in a reaction entropy is increasing, so we can say that the change mean subtraction of the lower entropy from the higher entropy. So it simply applies that when T approaches to 0, this S1 becomes equal to S2. Nernst Heat theorem has said this, because it has said that when there is no change in the entropy of the system, when the process occurs in the vicinity of absolute 0, means that when the process is taking place near about or round at the round absolute 0 temperature. Vicinity means the around. When the temperature is around to be absolute 0 or almost absolute 0, then the change in entropy is almost 0. Then the change in entropy is 0 at all. So we are writing this by applying the condition where the temperature is approaching 0, and at the end we are getting this form. Nernst Heat theorem, along with the study of the entropy, it also helps to determine the molar specific heat at constant temperature. Molar specific heat, we will derive it, understand it in the same way as we have studied about the entropy after knowing its formula. What is the formula for the molar heat capacity? It is equal to delta H divided by, means that change in enthalpy with the ratio of the change in the temperature at constant pressure. For the change in enthalpy, the Cp, the above equation will be used. The above equation is telling that the heat capacity, molar heat capacity, is equal to the enthalpy change with respect to the temperature change at the constant pressure. So when we apply the change factor, that is a delta to the heat capacity, molar capacity, and to the enthalpy, so the equation become in this way. In the vicinity of absolute zero means that when the temperature is almost or around about to be the absolute zero, the above expression will become in this way. So because just it is just that in the same equation we are applying the limiting factor. What is the limiting factor? We are saying that the temperature is approaching towards the zero, so that's why we are putting here limiting factor is that temperature approaches towards zero on the left and right both side. According to the Nernst theorem, we have said that the limiting factor T approaches to zero, del differential of the free energy divided by the differential of temperature at the constant pressure, that is also equal to zero, and the limiting factor T approaches to zero, differential and change of the enthalpy to the ratio of the differential of temperature at the constant pressure is also zero. So it means that the right side is becoming zero, only left side is remaining, that is to be determined. So here the need to be determined is that limiting factor is applied on the left side to the heat capacity, and we are saying that here the heat capacity is changing from one form to another. So it means that we will show here that the Cp2 means that the higher molar capacity, molar heat capacity, is being subtracted by the lower heat capacity. Lower molar heat capacity means that the first the molar heat capacity was lesser, then it got increased, and if we want to get to know the change in the molar heat capacity, it's clear that we will subtract the smaller value from the higher value to get to know that the change that has occurred. So it means that the change here, the delta, is being resolved by applying this form. Okay, so when we apply this form, we get to know that as the right side was zero, so we will put the zero in that in the place of that factor zero. So when we take the one factor on the left side, one factor on the right side, the negative sign is removed. According to the above equation, it's telling that the molar heat capacity at the constant pressure during any transformation at absolute zero remains unchanged. Means that when the temperature is at absolute zero, there is no change in the entropy, and there is no change in the molar heat capacity when the temperature is zero. Same we have observed in the derivation for the entropy as well as for the molar heat capacity, where it is becoming equal to zero. So the variation can be explained with the help of the graph. Graph is showing the change in the value of the Gibbs free energy, and then the enthalpy, it is showing that above the zero point, above the absolute zero, means that at the absolute zero point these two factors delta F and delta H are meeting with each other, are joined together, and with the increase of the temperature these two factors are coinciding, have left to be coincided, means that are going apart from each other, and then with the decrease of the temperature these two factors are coming to close each other. This is how, that is why we made this clear that delta F is equal to delta H when the temperature is equal to zero. In the previous whole derivation we have said this, in 2 days actually derivation we have said this, when the T approaches to zero, means that temperature reaches to the absolute zero value, this delta H and delta F will become equal. So that thing we can see from the graph also. See that at the zero value these two factors are coinciding, and when the temperature is increasing these two factors are going apart from each other. So that was all about the Nernst heat theorem.